Okay, section 3.2. Here we'll do examples of subspaces. So we've seen, a couple, three of them, the null space, right? So we had the null space of a matrix, the column space of a matrix, and the row space of a matrix. Those were three examples from the first video. But we have some others that we can look at. So, for instance, let's take, here's an example. If we take xy element of R2 such that x equals negative y. Okay, well, let's try the zero vector. Okay, this is in our subspace S, since 0 is equal to negative 0. So that was easy enough. Now 2 closed under addition. And so let's take x1, y1 and an x2, y2 are elements of S. Okay, and we'll let xy equal our x1, y1 plus x2, y2. Kind of ran out of room there. So now what we want to do is look at whether x is equal to negative y. And so if I start with x, then x, according to this, is equal to x1 plus x2. But x1 plus x2, x1 is equal to negative y1, and x2 is equal to negative y2. And so this is the negative of y1 plus y2, but that is just the negative of y. And so indeed, it's closed under addition. And then finally, scalar multiplication. Again, we let, say, at x1, y1 be an element of S, and we'll let t be an element of the real numbers, and we'll set our xy to be t times our vector x1, y1. Okay, and again, so we just want to look at x and see if it's negative y. So x is equal to tx1, but x1 is negative y, so that's t times, or negative y1, that's negative y1, but that's equal to negative ty1, which is y, and so closed under scalar multiplication. And there we have it. So that is indeed a subspace. Now, on the other hand, if we let S be xy element of R2 such that what I have here, x equals negative y plus 1. Well, this is not a subspace, so I should probably write example 2 up here. This is not a subspace since the 0 vector doesn't work, right? Since 0 is not equal to -0 plus 1. Okay, so the 0 vector is not an element of S, so not a subspace. So I showed by a counterexample to one of the properties of a subspace that it's not a subspace. Okay, example 3. Let's take symmetric matrices. Symmetric matrices. So here I'm in the space of matrices, not Rn, something like that. So symmetric matrices, and of course that means that A equals A transpose. So is this a subspace of all matrices of a n of size n by n? So we'll go with like n by n. Symmetric matrices size n by n. Well, how about one? The 0 vector. Sorry, 0 matrix. 0, I'm still going to put a line over it, and I'll put n by n. That is indeed equal to the 0 matrix that's n by n transpose. Not a problem there. Okay, 2, how about if I take an A1 and an A2 that are elements of my subspace S. Now, if I let A equal A1 plus A2, then we have that A is A1 plus A2, but A1 is the same thing as A1 transpose. A2 is the same thing as A2 transpose because they're in S. So they're symmetric matrices. And then that's A1 plus A2 transpose, but A1 plus A2 is A, so that's A transpose. So again, we got closed under our addition. 3, scalar multiplication, so I'll let A1 be an element of my subset S. Some T, an element of real numbers, and we'll let A equal T A1. And so now again, if I take A, that is just T A1. But since A1 is in S, that's the same thing as T A1 transpose, which is equal to, now this is a very subtle step here, but putting the parentheses around this T. It's kind of bad lowercase t's for both of these, but your textbook uses a T, so for the scalar multiple, so I'm using a T. And but then that's just A transpose. So again, closed under and scalar multiplication, SM. Okay, so there's something that's pretty related to what we're doing, but not quite what the textbook had really done so far. And this is example 4. All right, yeah, okay. So, did I write example in front of that one? No, okay. Example Example 4. Now, we'll really depart from matrices and all that. Let S be the set of differentiable functions on the real line, on R. Okay, so 1, how about f of x equals 0, identically 0? Sure. F prime of x is defined, so you get 0. So check. 0, the 0 function is in S. So, f of x equals 0 is an element of S. 2, so suppose I have g of x and h of x are elements of S, and I let f of x equal g plus h of x. Well, then f prime of x, we want to know, is that defined? But f prime of x is just g prime of x plus h prime of x. So defined. And so we have closure there, closed under addition. 3, if we let g of x be an element of S, and we say, well, f of x is equal to some t times g of x, for t a real number, then of course we know that f prime of x is just t g prime of x, so it's defined, and so we have closed under scalar multiplication. So there we go. There are a bunch of examples of things that are subspaces, and so we'll move on from there.